that particular functionality, then you can imagine the size of the input is this, and even if I assume that the weights, okay, or if I assume that the input is of binary size, let's say 0 1 0 1 0 1, all the inputs are of binary size, still that could be a combination of 2 to the power this size input. So that is the amount of combinations of weights that I could get in my neural network. So it's not a very small size value or size range. So how could I, because if you go back to the structure here, one thing I would like to make it sure here, I could get a very appropriate classifier or a neural network for this function just because these values were very, very appropriate. Because I had choose that let these values be 1 and 1. And if you see here, I am multiplying these values, and this I call them as a weight value. Okay, so I am multiplying the weight value with my input. So the weight values are being multiplied with the input. That means the weight values is going to identify how much of probability you are going to put on the output neuron, whether it is going to get fired or not. And if your weight values are not appropriate, then either your neuron might be fired wrongly or might not be fired. Okay. So these weight values that I am going to put as a synaptic weight between different neurons are very critical for me, right? So these values, how do I choose these values? Manually choosing for a simple network architecture is possible, but when your architecture becomes very, very complex, like this task, then it's not possible for a human to sit down and give some values there and then look whether he is getting an appropriate output and then decide whether his weight values were proper or not proper. Okay, so it's not possible for a human to sit down and pinpoint these values. So we need a learning mechanism. That is where the learning comes into practice. So whenever we have a neural network and we want a task, a input task that is little complicated for the network to perform, then we want that the network should do some learning. And what is the learning in a neural network? The learning is the discovery of these appropriate values of the weight, because I am repeating this, what a weight identifies how strongly a given neuron is connected to the next neuron. So if the weight is more, then it indicates that whatever signal is going to come here is indirectly going to get propagated to this next neuron, triggering him to get fired, and subsequently he might go on forwarding this signal to the next neurons and so on. So these weights are appropriate. If the weights are very, very low, then it becomes like an inhibitory. That means whatever input are being coming in to these neurons might not be propagated enough to the next neuron to get him fired. So this learning of the weight is very, very fundamental in a network, right? So how do we learn this weight? There are different mechanisms of learning weight for a given neural network. Keeping that aside, let me say you this particular thing here. For example, what you would like is, let's say you just have a output unit here, okay, and there are certain input units. Now when you look this particular structure here with 4 input units and an output unit, then we have certain considerations. What could be the considerations? We are assuming that the inputs could be of arbitrary real numbers. Okay, let the input be of arbitrary real numbers. The weights could also be of arbitrary real numbers. But in day-to-day practice of neural network, you will see that the weights are actually normalized between zeros and ones. Because when you are dealing with arbitrary real numbers, then your weight space becomes very, very large and very, very difficult to make your network converge in limited time. Okay, so usually we keep this weight normalized to 0 and 1s, but that does not limit you to having arbitrary values. Now let's say we are saying it this way. Now if in this classification process I just want that my output neuron should give me a 0 or a 1, that means these arbitrary real numbers of input together with the arbitrary real numbers of weight finally should be compressed down just to an output of either 0 or a 1. So you need a squashing function here, a function that squashes this entire set of input into an output of just 0 or 1. So what we do, we usually use certain squashing function in the final output of the neuron. And one of the squashing function could be your sigmoid function. Okay, so your sigmoid function might limit you between the values or in a range between -1 to 1 or in a range between 0 or 1. So the output always squash down or compress down your entire range of input just to a final output. Very briefly, if we try to understand it a little more clearly, let's say you are designing a network and you have these sets of features. Okay, these sets of features could be the features like, if I say you, okay, these are the different features which indicates, for example, whether a given object is a bottle or not. So I could say that let this be the length of the bottle, let this be the diameter of the bottle in centimeter, let this be the volume of the bottle, and so on. Okay? So if I say if the shape is of this size, then I don't consider that as a bottle, and if the shape is of this size, then I consider that as a bottle. So I get some classifier output values here indicating zeros and one. That means there is a presence of a teacher here. So given certain values of a bottle, the output is already known whether those values corresponds to a bottle or those values do not correspond to a bottle. So I have a presence of a teacher now, and the presence of the teacher is a class for us. So this type of learning we call as a supervised learning. That means we have someone present to guide us whether the input values corresponds to that particular class or not. Okay. Now, when you are designing a neural network that is of supervised in structure, so whenever you are saying that it is a neural network trained with supervised type of approach, then your data record need to have this output level. That is the primary thing that we usually consider. So let's say you are designing this neural network and you start training the neural network. So how do you start training the neural network? One way could be you start assigning certain random weights, okay, to all of these connections. Okay? So your random weights could be something like this. Sorry, your random weights, I have not put it here. So your random weights could be anything here in all these in all of these connections here. And your input is 1.4, 2.7 and 1.9, 1.4, 2.7 and 1.9. Okay? You are expecting that when you give this input to your neural network, the neural network should give an output 0, because I am assuming that my neural network is already learned or maybe it is learning. So I expect the neural network to give an output 0, but I found that it gave me an output 0.8. That means I get an error value of 0.8. Why? Because the output is 0, the actual output is 0, but the obtained output is 0.8. So it is like, let's say 0.8 minus 0, you get an error of 0.8 values. Now, based on this error, we say, or we can remodify our network based on the error. Okay. Well, when I say that I am remodifying my network, that means I am remodifying the weights values here, because the weights finally are influencing what is the output going to be for given input. Okay. So what could I do? I could break my old weights on my neural network, and then I can start reassigning my weights, and then again I start verifying. Okay, I again start with some new instances. Let's say I give this now 6.4, 2.8, 1.7. What is the output I'm getting? I'm expecting an output of 1, but I got 0.9. So I got an error of 0.1. That means error is coming down. Why? Just because I am readjusting my weights appropriately, so that eventually with more and more input instances, overall the error of the network reduces. That is my objective, okay, as I proceed. So I go on comparing this way, again I go on readjusting my weight and so on. Finally, what you do? You go on training your neural network practically with thousands of instances. Okay, so whenever you are, let's say, designing a neural network for image recognitions or for let's say object detections, we feed thousands and thousands of inputs vectors to the neural network, so that he becomes more and more and more informative about the input representations. Okay. Now let's say if this neural network, I'm assuming, is for classifying whether a bottle is 0 or 1. Okay. So it could be something like this. All the orange instances indicates that's a bottle. All the yellow instances indicates that's not a bottle. So initially with very random weight. With very random weight means you started the neural network in a very raw form. Okay. So when you started the neural network in a raw form, your neural network could perform something like this. Okay. So maybe some of the instances were classified correctly, some of them were not classified correctly. So if you start looking the neural network as a classifier, then you get the performance in this form. As you go on refining the neural network, then your classifier, the neural network as a classifier, go on varying its performance. So slowly it improves, and finally with hundreds and thousands of instances, you might get a representation of this form. The neural network could classify all the instances very, very appropriately. So one thing that we got to know here is that the size of the input instances is very, very important for us. So more information you have for training.
Sorry for little interruption, Dr. Sharma. You have you are on the verge of the deadline. So can you wind up within?
Yes, yeah, I'm winding it up. So the same thing could be like for your, let's say you can have a neural network design for recognizing, let's say, sets of inputs here. Okay. So let me very briefly give you certain ideas here. If I show you a picture here, for example, okay. So if you look this picture here, this could be one neural network. So whenever you are feeding, whether you would like to know whether a given input has the size or the face of a person or not. So you are designing a neural network where you give the input the image which is in pixels, row and column wise. Then you have the layer here. So let's say this particular layer is responsible for detecting the horizontal edges or the vertical edges in your input images. Okay. So it is only responsible of detecting all these horizontal and vertical or diagonal edges in your images. The next layer will be responsible of combining some of these edges into higher dimensional features. So for example, if you consider a nose, your nose will have a vertical edge and a horizontal edge. Likewise, your eyes could have a number of horizontal edge and a circular shapes. So all of these neural network are, or the layers in the neural network are being designed for different purposes. Okay. So here this particular layer could be used for detecting all the edges, could be horizontal, diagonal or vertical. These layers here could be used for combining some of these edges to represent some higher dimensional features. So you start getting the shape of a nose. Again, in the higher layers, you start combining all the lower dimensional features until you start getting a face, and the output is going to say 1 if there is a face present in the input image, and the output is going to be a 0 if there is no face present in the input image. Okay, so that means you can design a neural network, and each of the layer in your multi-layer neural network is having a special functionality of identifying certain features present on your input. And as you go towards higher in the network, each of these lower dimensional features are being converged, finally being mapped to your final object, and then your neural network understands or classifies whether that particular input, expected input, is present in the image or not. Okay. So this is how we go on training a multi-layer network. I'm trying to be very, very concise here. Okay, so if I very quickly take you to very, recent work that people are trying to do the forensic analysis, either in seeing how a neural network could be used to create certain deepfake videos, or how it could be used to identify whether a video is deepfake or not. So if you could see here, if you see this particular video here, you have Vladimir Putin and Barack Obama. Okay, so this is the video of Barack Obama. Now using neural network, we can entirely map, okay, the movement of Obama. Okay, all his movements can be mapped into these still images of Vladimir Putin, and in fact you can see a video of this one. So it becomes very difficult. So this is a fake video now being created by tracing out the movements of this particular source video. See, so you can have a video here, you can have an image here, then using a neural network you can create the deepfake videos, and finally you start getting a video of this one where you'll see that Putin is exactly speaking the way Obama is speaking. Okay. So this is somewhere where people are trying to concentrate, given a video, whether a video is fake or it is not fake. So that becomes one dimension that people are presently working in the cyber forensics domain. Human surveillance, of course, this is a very well established field in the machine learning. So lot many algorithms you'll find in today's date. For example, Yellow version 5, which works very, very precisely with identification of humans. So human surveillance is a well established domain in today's field. And if you look, the ladder is really, really infinite. Okay? The applications domains are really infinite. You just give one step in one part of the ladder, and then you start seeing lot many other steps yet to be explored. So it's just that you give a step today, and all other steps in the ladder become visible for us to apply. So thank you. This was very, very brief about me trying to take you from the basics to, let's say, the present day applications. Of course, 20 minutes is not enough for a good understanding of it, and maybe many of you are already working on it, or maybe for some it was very new, so it could be an idea for you to use it in your applications domain. If you go to, let's say, nanoscience, in nanoscience you're dealing with signals, so you get a large spectra of signals. So these signal parameters you can very well design a classifier system for the signal parameters using a neural network, or you can also analyze these signal parameters using machine learning techniques. So thank you all, and I would like to welcome for certain questions or any doubt.
Thank you, Dr. Sharma. It was a nice talk on neural networking, and you had given us a preliminary idea about how this can be used for detecting fake videos or human movement, something like that. Okay, so we have a couple of questions from Mr. Shubhranshu Bose and Dr. Shobhan Ghosh. So I request Mr. Bose to ask a question.
Thank you, Mr. Sharma, Dr. Sharma. I want to ask how to choose the feature for a neural network.
Yes. So whenever I'm applying a neural network for a given domain, so for me what is important is to understand what input parameters are important for me in that domain for my output. For example, let's say because I had seen Sayan working on so many projects. Let's say we are trying to design a neural network classifier, trying to identify whether all the sensors put on a human body corresponds to movement of his arm or movement of his hand or movement of his feet, let's say. So I'm getting huge amount of data from all of these sensors, continuous data, and I would like to design a neural network which has the ability to identify that presently the significant data that is coming in that corresponds to the movement of a leg or that corresponds to the movement of an arm and so on. So in that perspective, the features that could be important for me is the different voltages. So it could be my voltage of a signal that is being generated by different movement of the human body. So for me in that domain, the features become important. What features become important for me is the time features. So that is one feature, let's say with respect to time. What are the amplitudes of the signal generated? So the another features could be, let's say, y, which is my amplitude. So very low features. If you consider the image of a person, then how can I know whether a given input image has the face of a person? So to know whether there is a face of a person, I should know that at least there are two eyes present, there is a nose present, there is a lips present, and there are 2 ears present. So for me, it becomes important that at least there should be a nose present. So when I say there is a nose present, that means like I had shown you one neural network. So how the neural network is going to identify the structure of a nose? So I design a neural network such that I identify that, okay, that there should be a nose present, there should be an eye present, there should be a lips present. So for me, for a human face identification, those becomes my important features. Now again, one more thing, when you are dealing with very large size features, let's say 150 features you have, all the features may not play very important role. Let's say the color of a person is not very important to know whether there is a person present in the object or not. Whether that might be a dark guy or whether that might be a white guy or that might be a mild skin color guy. The color is not very important for me, but the color feature is also present. So I can also discard features which are not very significant to me. So there are algorithms that allows me to discard features so that I don't overburden the neural network unnecessarily with extra features. So that is why when I am not very sure which features are important for me, which are not, then I take the help of the feature reductions algorithms. But when I am sure, then I can manually intervene and I can discard all those features.
Thank you. I think this discussion can be taken beyond this today's event because we are already running out of time. And one quick question from Mr. Dr. Shobhan Ghosh.
Hello. Yeah, thank you, Dr. Rupam. It was a very nice discussion actually going on. I have this question, what you were telling just now actually, in reply of Subhranshu, that yes, suppose the complexion and some of the features which are not so much important, you are going to discard those from your parameters, right? Now the point is that when we go for some kind of discard, we have so many small potentials, small noise even, right? Which is not exactly related to the main parameters of the algebra, but that also contributes. So my point is that that can introduce a lot of error, right? So in that case, whatever the exact thing we are looking for, that may be deviated. What will be your answer regarding this?
So, if I'm not mistaken, if I have understood the question appropriately, is it again like you are trying to know how let's say certain features which are not very important, but when we discard, then still our output get influenced. I mean, so are you trying to ask that?
True.
Yes.
We may get some erroneous results. That's what I'm asking.
Yes, exactly. So, like I had already told you, see, when in some of the practicals related to computer networks, when I do, we find that some of the features are not very contributing. But when we discard, then a point comes where the discarded features tries to prove to be critical to us. Most of the time, let's say 80% of the time, we thought that those features are not really important for us, so we discard it. And eventually we find out just because we don't have those features, we ended up in some certain false positive cases. So what we do here is, let's say, so that is what we are saying. You could also have a stack of learning. Let's say in one of the learning, if you find it that when you're discarding the features, you are sometimes you're not getting the appropriate output. Then what we could do is you can have one learning above the another. So let's say this in the first learning you are filtering certain things, and when the output is not appropriate, then you can have the second stack of learning put into it. We call those as an ensembling process. That is one. Or otherwise, you also consider your features that were less significatory, and then try to see or try to assign lower and lower weights to those features so that they do contribute but not significantly as compared to the primary features.
Yeah, that's
Like
what
we
I
had
wanted.
seen,
That's the
like we had seen how the weights are going to influence the output. So features which are not very contributory, let they influence the output less significantly compared to the features who are more significatory to the output. So we can also
Yes,
have
we can
a design on that way.
Yes, we can get this. I think this discussion can be taken beyond this meeting also. We have your email ID, we have all this contact
Right.
information. So I ask all
Thank
of
you,
you
Dr.
if
Sharma.
you have significant questions. If you have some queries, then you may contact Dr. Sharma for your queries. So thank you, Dr. Sharma. It was really a nice talk on neural networking. I personally learned a lot of things from you. Thank you.
Thank you, and thank you once again for giving me this opportunity. And we hope we can always meet and have our all we can have a interactive, competitive research amongst this group, and that will help all of us. So thank you once again, everyone.
Thank you. So our next speaker is Dr. Satyaki Kaur. So he has already joined. So let me give a brief intro of Dr. Kaur. So Dr. Kaur is an assistant professor at AKPM Vidyalaya at West Bengal, and he has received his master degree from JNU in physics, and he has earned his PhD from Florida State University, USA. He mainly works in the field of theoretical condensed matter, and he has received his several awards as well, fellowship, just like your graduate research assistantship, graduate teaching assistantship, etc. And he has also attended many conferences, just like ATS meeting, etc. Like, and he has also authored many reputed publications and book chapters also. So today he will be discussing on the quantum oscillations in modal time semi-metals. So I request Dr. Kaur to start the talk.
Thank you, Dr. Shahanban. That's a very kind introduction. I would first like to say thanks to the organizers for basically organizing such a nice conference, and also for inviting me to give a talk here. So thank you so much. So I'll just right away go to the talk. let me first, so that there is no streaming problem, let me just stop the video and share the presentation. Okay. Okay, so the title of the talk is Quantum Oscillations in Topological Nodal Line Semimetals. So this is basically based on these two papers, recent papers of mine, and so let me just first go to the contents of catalog. So basically the contents is that will firstly very briefly discuss about what is quantum oscillations, and then what are nodal line semimetals, and then we'll talk about how these two are connected, and then briefly talk about simple continuum model of the nodal line semimetals. There we'll talk about Fermi surfaces and Onceler relations, and then two situations will be discussed here. First, when the magnetic field is perpendicular to the nodal plane, and the other one is when the magnetic field is in the nodal plane. So in this two scenario, we'll I don't know whether we'll have time, but if time permits, we'll talk about the density of states, reduced effective masses Zeeman effect, and then in the later case, when my field is in the nodal plane, there are some topological oscillations we can find at low energies. So we'll talk about that also, and the possible topological transitions, and then finally summarize. So when we talk about quantum oscillations, basically what we have to consider 2D or 3D systems. Basically 3D system we can consider, and then we have to vary the magnetic field, and then from there things start. So we first take a look at the 2D electron gas. So in a 2D electron gas, so there are free electrons moving around in a plane, and then if you have a magnetic field in the perpendicular direction, then the electrons make these cyclotron loops. So these circular loops you can have, and there's a frequency for that. The cyclotron frequency omega c equals E over A. You can take a look at this cartoon to see basically what is happening. So in the bulk of the system, there are these cyclotron orbits, closed cyclotron orbits for the electrons, and at the edges, those cyclotron orbits cannot complete their loop, and so there is some skipping orbits, and then electrons can move along the edges and give some conduction. So so this is the pretty much the picture. Now if you go to the momentum space, you will see that there is some lambda quantization that takes place in these systems. So first of all, if there is B equals 0, means field, there is no field, we have this p square over 2m Hamiltonian. It's a free electron Hamiltonian, and then the wave function will be like plane waves, and then we have energy given like that. So for this energy, you can have these constant energy contours, which are concentric circles in the momentum space, and these blue dots over here you can see, these are the allowed k vectors, and the spacings between them depends on the finite dimension of the system constant. So then if you plug in the field in the perpendicular directions, we have to consider the PL substitution. So P becomes P minus EA, where A is a vector potential, and then with that the Hamiltonian changes. The Hamiltonian becomes just like a 1D simple harmonic oscillator in the y direction. It's like that, and then which has an energy n plus half h plus omega c. We know omega c is the same omega c as this one, cyclotron frequency. But then this y naught over here, this is not a constant, this is px over EB, px being the x component of the momentum. So because this is not a constant, so there is huge degeneracy attached to this each n value, which are called the lambda values. And then if you go to the momentum space, you will see there's a complete rearrangement of the k vectors, k allowed k points. So there are these concentric circles corresponding to different n values, and all the allowed k values, k points are now sitting along this circumference of these different lambda levels. So that is the lambda quantizations. Now if you add a third direction for a 3D electron gas, then what happens? This 2D cyclotron loop that we had, they advance forward in the third direction. So it's like a helical motion. But then if you go to the momentum space, you have to consider the semi-classical equations, and then from there you can see in the momentum space, these electrons actually you can still doing this 2D cyclotron motion, but then now they are having they can be in different parallel planes. designated by different kz values. Now this kz is the new parameter we have because we are considering 3 dimension. The energy is now this. Previously we had this thing, and then we have to add this part. So now here, if you can see this cylinder kind of thing. So all these cyclotron loops that you can see, they correspond to the same radius. So they have the same n values. The same n values they have. So this is called a Landau tube. They correspond to one particular n value. And this circular cut you can see here, this is a cut of the Fermi sphere. So the Landau tube which is inside that have occupied states. So if you consider the Landau tube portions which goes beyond that, then those will be unoccupied state. It's according to the zero temperature picture. So now there can be different of such Landau tubes for different n values. So this is the Fermi sphere, and there are different Landau tubes you can consider. And then now if you change the magnetic field, as you keep on increasing the magnetic field, these Landau tubes blow up. They becomes fat and fat, more and more fat. So it's like that. You are increasing P, this becomes larger and larger, and at one point of time, the dimension crosses the Fermi sphere dimension, and then at that point there will be no more occupied states at that Landau level, Landau tube. Now let's consider these two pictures here. So this is one Landau tube for one particular n value, and then we are considering one energy shell between E and E plus DE, and we want to calculate the number of electrons which are in this energy range in this Landau tube. So those basically correspond to these two shaded region you can see, and the electrons sitting there has that those are in that energy range. So the density of states will be proportional to the area of cross section of these two shaded region. But then if you now keep on changing your magnetic field, keeping your energy fixed, or if you keep your magnetic field fixed and change your energy, in either case you can have a situation where the extremal area cross section of this energy shell becomes same as the area cross section of this Landau tube, just like in this picture. And then when that happens, you can see you don't have these two separate shaded region, top and bottom, but rather at the center you have a huge large shaded region. So there will be much more electrons which have energy between E and E plus DE in these situations. So in this case, the density of states will shoot up to a very high value. So if you keep on changing your magnetic field for different Landau tubes, for different n values, these kind of situations can occur periodically, and then in the density of states you can get a plot like that. So here we have shown one particular P value and changed energy, and then for each Landau level energy, the density of state shoots up, and then it shows a 1D like decay, and then for the next available Landau level energy it again shoots up. So this periodically goes on like that. And then instead of that, if you keep the Fermi energy fixed and vary the magnetic field, you will still see oscillations. And that is the quantum oscillations we talk about. And then it turns out, if you plot that with 1 over B instead of B, then it has a constant periodicity. So that corresponds to the quantum oscillations frequency. So this is one typical experimental picture that I just actually took from Ascroft Mermin's book. So this is magnetoresistance plotted for a compound, and then as magnetic field is increased, the quantum oscillation grows more and more, but you can see the distance between two consecutive peaks also growing. So they don't have constant periodicity. But if the same data, if you just plot it with 1 by B, 1 by T plus 1 by B, then you can see they have constant peak. So that's what we just say. And this can be backed up with equations also. So for a Landau tube, typical area you can write as pi k perpendicular square, and then it has this expression. You can write it as from the Onsager relations also. Both are same. Only difference is that they have here a factor gamma in place of half here. That is because this is more general. There can be situations where this can be different from half. So see that this half is coming from this harmonic oscillator energy in plus of h plus 1. So now, this is the area of the nth Landau tube, and if we want to have the density of state peaks, then we have to consider the extremal area of cross section of the Fermi surface also. We can call that SE, and then we have to get the period of these quantum oscillations. So we have to see what is the change of magnetic field for which two successive such peaks I can get. So we have to consider two successive Landau tubes, n and n plus 1 say. And And then for that, we have to see what are the B values. One is Bn, one is Bn plus 1, you can say. And then if you want to calculate the difference of that, you will see that that's not a constant. That depends on both Bn and Bn plus 1. But then if you calculate the difference between 1 over inverse of them, like 1 over Bn plus 1 minus 1 over Bn, that turns out to be a constant, which is this constant. This depends on only AC, which is a function of Fermi energy. So that's basically saying that if you the quantum oscillation data, if you plot it with 1 by B, then you can see a constant periodicity. So this is very simply saying quantum oscillations in electron gas system. Now we have to consider the nodal line semimetals. So this is a typical energy band diagram for metal, insulator and semiconductors. For semimetals, basically there is some point touching. So the two conduction and valence band touches in along the point where the density of state is very small. Now for nodal line semimetals that we are interested, this kind of touching are linear in fashion. So so this is a linear crossing between conduction and valence band. And then whenever that occurs, this is special because the mobility of the carriers electrons becomes very huge at the crossing points in this scenario. And then also because it's linear, we have to consider Dirac equation to study such systems, and then we have Dirac Hamiltonian. Like for 2D, for graphing case, we have a Hamiltonian like that, and for 3D we have a similar Hamiltonian. That also. For 3D we can have wild semimetals where this in the 3D Brillouin zone they touch linearly at discrete points. They're called wild points. And the system of interest in our case is the nodal line semimetal. There actually this linear crossing occurs, but not at discrete points, but along a closed line of loops in the Brillouin zone like that. These are called the nodal loop or nodal ring. Now they have some special characteristics, like these nodal loops are very robust. You cannot by some local deformation wipe out this nodal loop. You can change the shape of that, but you cannot just completely wipe it out because there is some symmetry attached to that. This is symmetry protected, and the symmetry can be inversion symmetry, time reversal symmetry, etc. These are typical systems which show these nodal rings in their spectra. Now they have some non-trivial topology attached to this. So basically, how that is calculated, we have to go to the momentum space and do some mathematical construct. This is called Berry connection, Berry curvature, and Berry phases. I'm not going in detail of all those things, but imagine this is the nodal loop in the momentum space, and then if you have a electronic pathways in that system that rings through that nodal loop, and then you calculate this quantity Berry phase, which is a closed line integral. So if you calculate this Berry phase, you get a non-zero value, and that is an indication that this system has a non-trivial topology that is related to Chern number, which is the topological invariant of the system. Because in this kind of nodal line semimetal systems, we can find electronic pathways of this fashion. That's why it has some non-zero topology. But the thing is that their surface states, which are drum head surface set, which it looks like a drum head, they don't always show topologically protected behavior. So typical experimental tool like RPS sometimes cannot very nicely determine the topological nature of this kind of compounds. Rather, if you consider quantum oscillation measurements by drawing something like Landau-Fan diagram, we can very easily calculate the Berry phases, and we can see whether that is zero or non-zero. And then from there we can understand the topological nature of such systems. So that's why this quantum oscillation measurement is very special for this nodal line semimetal systems. That is one special connection between these two. Now, if we go to the simple models, this is the typical continuum models of the nodal line semimetals. So this is the typical Hamiltonian. This is 2 by 2 Hamiltonian. These sigma matrices are coming from this orbital degrees of freedom, and this is the energy expressions. Plus minus are called conduction and valence band. And then you can see here the nodal loop is basically a circle in the kx-ky plane. You have to put kz0 here to get that. That actually corresponds to epsilon equals to 0. Now, if you put a magnetic field there on the perpendicular directions, you have to again do the period substitution, and then if your Hamiltonian gets modified, and finally this on the Landau level basis, this is your Hamiltonian, that's the energy expression. Now we have to take a look at the Fermi surfaces. When my energy is 0, the Fermi surfaces actually falls on top of that nodal loop. So basically, this is a closed line. at energy equals to 0. If we keep on increasing my energy, chemical potential, we will get torus-shaped Fermi surfaces that surrounds that nodal loop. And then if you keep on increasing your energy, that torus becomes more and more fat, and the hole inside becomes smaller and smaller, and at one point of time there will be no more inside hole there, and it will be a drum-shaped Fermi surface. So that's a clear change in topology. So then let's consider a typical low energy Fermi surface, this torus. So this one, and this dashed black circle you can see here, this is the nodal ring sitting inside. So for quantum oscillations, studying quantum oscillations, we have to have magnetic field in one particular direction. Let's say first of all magnetic field direction is in this direction, the z direction. So for that we have to consider what are the extremal area of cross section. So there are two extremal area of cross section, and that occurs when my kz equals to 0, and those two are these two yellow circles you can see here. But the thing is that if there are some electronic pathways along this either of these two yellow circles, they never rings through this nodal loop sitting there. So that's why if you calculate the very phase, you get a 0 value. So the magnetic oscillations are trivial. But then if my magnetic field direction is in the x direction, let's say in this direction, then we have to put kx equals to 0, and then these blue circles you can see, those are the extremal electronic pathways. And then if the electron goes around that, and then if we calculate the very phases, you see that this actually rings through this nodal loop sitting here. So the very phase will be non-zero, plus or minus pi, and that's why we have non-trivial oscillations for this case. So this is the difference between quantum oscillation along for field in two different directions, z and x. And then again these are the equations, and then this is the Onsager relations where we have this gamma factor we mentioned before also. This gamma is related to this very phase gamma b in this fashion. So once we calculate this gamma, we can calculate the very phase gamma b, and then we can see whether this is 0 or not 0. Now, because we are trying to access the extremal area cross section, here in this expression of energy, we have to put kz equals to 0, because there we can only get this extremal area. So that simplifies the energy expression. We get this kind of energy expression. We can plot that versus b. So this is E versus b. So we can have a pair of branches coming from this plus and minus spin factors, and the same for different n values. And then if you consider different Fermi energies, let's say here mu1, mu2, or mu3, and those lines you can see Fermi energy lines, they cut these dispersion lines at discrete points corresponding to some different b values. At those b values, we have this extremal passing of the slender tubes. So if you collect them branch wise, let's say for the all positive ones, and then separately from the all negative branches, if we collect them all and then plot them, put them in a 1 by b versus n diagram, which is called a Landau-Klein's diagram, we will see they all orient along the line. And that should be because this is coming from this Landau-Klein, this is coming from this Onsager relation. This equation is the Onsager relation written in a different fashion. So they are oriented along the line, and then wherever they touches all these lines is one particular point. And then knowing that point, we can calculate this gamma. You can see also from this. So in this case, turns out this gamma is half. And then if you plot half here in the gamma, you can see the gamma b, which is the very phase, that comes out to be 0. So as expected, in this case, when my magnetic field is the z direction, my very phase becomes 0, and the magnetic oscillations is trivial. Now, one thing I am going to say here, that here in this slides we are just talking about this constant Fermi energy lines like mu1, mu2, mu3, etc. as I am changing this magnetic field. That actually doesn't occur. When you study the magnetic quantum oscillations, actually these mu lines are also fluctuating. That should be because this is a dynamic picture. The Landau tubes are always growing as you are increasing the magnetic field, so you cannot expect the mu to stay at a constant level. So you can also calculate that. You start from the thermodynamic potential and then take a derivative of that with respect to chemical potential to get your number of electrons and get an expression of that. And then if you now from in this expression, if you change your B, for the constancy of this n, you also have to change this b. So numerically you can evaluate that, and this is a typical plot shown for three different capital N values, and it shows that the fluctuations in mu or EF grows more, so they have more amplitude as the amplitude increases for large values of magnetic field. And also because we are plotting with 1 by p, you can see kind of constant periodicity in this between these oscillations. So so that is the thing. So this is we need to also see when we study this quantum oscillation properties. Now this is I am going to skip because I think we will not have time to talk about this thing. We can come back that later if we have time. So the next thing is when my magnetic field is in the nodal plane. When my magnetic field is in the nodal plane, let's say in the x direction, then the problem is more trickier because the xy symmetry of the problem is lost because the field is in the x direction. So but still we can write the Hamiltonian expression after doing the pure substitution, which looks like that. And then to get the energy spectrum, now we can do it numerically. We can do exact diagonalization. This is a typical plot of exact diagonalization result. And then from there you can see the extremal area of cross section appears where this del A and del Px becomes 0, and that occurs at Px equals to 0, just like, or Kx equals to 0. Just like in the previous case, we are considering Kz equals to 0 plane. Here we have to consider Kx equals to 0 plane to access the extremal area. So we put Kx or Px equals to 0 in this problem, and then see that the Hamiltonian, first of all for B equals to 0, has some energy minima at these 2 points. Those are Dirac points because this linear crossing of conduction balance band. And about those 2 points, the Hamiltonian is like an anisotropic Dirac Hamiltonian that you can find in the section like this. Then if you plug in the magnetic field, then you get an expression for the Hamiltonian with magnetic field like that. So your B is here in this omega c because it's EB over. So now we'll just keep that there right now. We can always numerically solve it. We can do the exact diagonalization, and this is the spectra shown here. So it shows that for small b values, there are double degeneracy in this problem. And then as b is increased at one point of time, each of those doubly degenerate bands get split up into 2 non-degenerate lines, as you can see here. And this is happening for both positive and negative energies. Now, to understand that why this thing is happening and how to explain that, what is generally done is that this Hamiltonian is squared up. See that this Hamiltonian is not diagonal because it has sigma z is that it has this sigma y part. So this is not diagonal Hamiltonian. So, but if you square it up, it becomes a diagonal Hamiltonian, and then that diagonal Hamiltonian turns out to be just like a nonlinear harmonic oscillator Hamiltonian, which has a kinetic energy part and a potential energy. That potential energy is like a double well potential, which looks like that, which has 2 potential wells like this. Now, when my magnetic field is very small, the distance between these 2 potential wells is very far, and then you can treat them independently. And then each one of them, for low energy, you can consider that to be a simple harmonic oscillator, and both of them has the same energies. So you can have energy matches at low energies. Then when there is energy matches, you can get double degeneracy, just like seen here. But then as your B is increased, then these 2 wells becomes very close to each other, and then that independence between these 2 are lost, and then the degeneracy that it was enjoying before for small b values will no more be there, and then it gets split up into 2 non-degenerate bands like that. And then also from the energy expression you can get from this diagonal Hamiltonian, which you get after squaring up, you can take a square root of that to get an expression of the energy for our Hamiltonian, which is written here for low energy. Epsilon n can be written as with some prefactor square root b and square root n. So this is not linear with b, and this n you can call that lambda level index. Now also we can talk about topology in this problem, just like we mentioned before also, with some argument. So here again this is the energy diagram, energy spectrum drawn with P. So let's consider two energies, two chemical potential, mu1 and mu2. A typical small energy, small Fermi energy, and large Fermi energy, which is above that splitting of the bands. For small energy, mu1, if you draw the Landau-Venn diagram, you can see just like before, they are oriented linearly, but then they all meet at a point which leads to a gamma value which is 0. Now when this gamma is 0, if you can plug that in the equation of gamma b, that will turn out to be non-zero, plus or minus pi. So the Berry phase becomes plus or minus pi. But then if you are at a large energy, mu2, and then in the Landau-Venn diagram, you can get the n-intercept is now half, just like before in the previous case we mentioned. When this thing is half, again if you plug that in that equation, you get the gamma b to be 0. So in this case, Berry phase is 0. So at low energy, you get non-trivial topology. At high energy, you get trivial topology. You can see that from here in these pictures also. This is a low energy Fermi surface. This is a high energy Fermi surface. It's a torus. It's a drum shape Fermi surface. Now in this one, if you just do a kx equals to 0 cut, plane cut, you get these two Saturn loops. And the direct points we just mentioned, they are sitting inside these two Saturn loops. So if we consider either of these two Saturn loops and consider the electronic pathways along that and calculate the Berry phase, you get plus pi or minus pi, which points to non-trivial topology in this case. But at large energy, because we have this drum-shaped Fermi surface, and if you do the cut, you get a very large Saturn loop, which includes both the direct points. And then if you do the electronic pathways along that and calculate Berry phase, you get a result of plus pi minus pi equals 0. So this is a trivial oscillations.
I will request Dr. Kaur to wind up because we are running a little late.
Okay. Just one slide there. So this is the last slide. So this is basically in this case when my magnetic field is in the nodal plane, because we can get both trivial and non-trivial oscillations. So we can consider a range of magnetic field and then repeat that by some driving, like some periodic drive. You can consider a periodic drive in some particular range, and then if you can just repeat these changes in P, and that there by doing this driving you can access this two different topology and transitions between them repeated. So that we can do. And so this is a nice thing for this problem. We can consider this topological transitions to access periodically with such periodic drive. And then another good thing is that here, because these two bands are, all these bands are very close together, and then there is a periodic drive present there, we can consider the interlevel electron transfer, just like a Landau-Zener problem. The electron can transfer from one to the other one, and then we can see how in this non-equilibrium setup the electron conduction can change. So that kind of thing also we can study in these problems. So these are pretty much all the other things what we couldn't talk about because of the time constraint. So basically in the summary, we just say that we just talked about nodal line semi-metal and quantum oscillations, where we consider the variation of strong magnetic field. The two things we considered when my field is perpendicular to the nodal plane, where we see the magnetic oscillations is trivial, and the problem can be completely analyzed analytically. The other one is when magnetic field is in the nodal plane. There the symmetry is lost, so we have to we resorted to numerics, and then we have seen that at low energy the magnetic oscillations are topologically non-trivial, while at high energies we again get the topologically trivial magnetic oscillations. And then in this case also you can consider a periodic drive for magnetic field, and with proper parameters chosen there, we can see the topological transitions to occur periodically in such systems, and then we can also consider the interband electron transfers there, and then see what other non-trivial physics it can lead to. So thank you so much.
Thank you, Dr. Kaur, for your interesting talk. So the talk is now open for questions. We can